Today, I'm going to share our work DISSECTOR on input validation for deep learning applications by crossing-layer dissection. As we all know, deep learning applications are very popular in many areas. However, due to their naturally imperfect accuracy, their possibly wrong predictions may lead to runtime reliability issues and cause some tremendous disasters. We ascribe this to deep learning applications' differences from traditional ones. For traditional applications, there is a clear specification for its logics and can be used for testing and deployment. It could be very easy to identify some wrong behaviors. However, deep learning applications logic is generalized from large-scale samples and there is no clear specification. This makes it hard to examine and identify the wrong behaviors. Therefore, our focus today is how can we assure such deep learning applications reliability specifically. To do so, we consider a fault-tolerant way. That is, if any unexpected input is fed into deep learning application, how can we allow it to still behave well? We consider that for a deployed deep learning application, it has its own handling capability. For an input within the capability, one can expect it to work well. Otherwise, one can also choose to isolate such input to avoid possibly wrong decisions later. Therefore, in a fault-tolerant way, our problem can be transferred to a typical input validation problem for identifying within inputs. Specifically, our hypothesis is that for the kernel deep learning models in deployed deep learning applications, it has its own model handling capability scope. Inputs within such scope usually expect high accuracy. Inputs beyond such scope may cause dramatically decreased accuracy. Therefore, our real problems can be now, how can one distinguish that within beyond inputs well at runtime? We consider the distinguishment should be both effective and efficient. Concerning some existing practice, there are some work that address similar inputs distinguishment problem. For example, some work targets on OOD identification and choose to identify them by natural confidence score. Although this treatment is extremely efficient, it lacks sufficient effectiveness. Some techniques target on adversarial or corner case identification. They take some detailed treatment for nice effectiveness, but tend to be time-consuming and not efficient enough. We try to address our problem and balance its effectiveness and efficiency at the same time. Therefore, we actually seek for a lightweight and effective heuristic idea. In this work, our idea is within input is the input that corresponds to an increasingly consistent prediction process. To better understand our idea, we illustrate using a daily human recognition thing. Here, there is a guy walking closer and closer, and we are actually trying to guess who is this coming guy. Here are two different recognitions. Although they both get the final B result in the guess, they actually differ from each other. The above one is more fluctuated. We can be easily confused during the process. The below one is much more smooth, and we can find it more trustable. Here, this naturally maps our idea for identifying the within input. We can observe that such trustable recognition equals the increasingly consistent for within input. In practice, this is because one naturally gains increasingly confident to its recognition within a gradually close distance. After illustrating our idea on a daily thing, we now map it into the deep learning prediction thing as we expected. The both things share a similar step-by-step guess. They both target on giving the final prediction with guesses gradually. This makes the mapping quite straightforward. In the deep learning thing, the input picture is projected along the deep learning models and gets its final result as stop sign. Here are two different guess profiles. The above one keeps inconsistent and the below one is increasingly consistent. This exactly suits our heuristic idea. We similarly consider it to be more trustable. and the below input should be more within. In our study, over 95% high-accurate samples share such increasingly consistent gas profile. Then, in our approach, there are naturally two tasks. First, given any input sample, how can we obtain its gas profile? Second, based on such profile, how can we measure its gas consistency? First, for the first task, getting the gas profile. Its final gas is straightforward and given as a prediction result, but its intermediate gases are not easy. We actually first dissect the deployed deep learning models into a list of partial models for each layer. Each partial model is a submodel that links the formal deep learning models until the layer with a newly trained LR structure. After that, these trained submodels can be directly used at runtime for any sample to get its specific intermediate gases towards the final one. Then, task 2, with the preparation of the gas profile, how to measure its gas consistency. We consider to measure each gas uniqueness and combine them together to get the final score of the gas consistency. For each intermediate gas, we measure its uniqueness. It actually contains two cases. If this specific intermediate gas equals to the final one, we measure the range between it and the second highest label. The larger range, the better uniqueness. Otherwise, if they are not the same, we measure their range between each other, and the larger range, the worst uniqueness. Generally, such measured uniqueness score represents how much this intermediate gas supports the final prediction. Then, after obtaining the uniqueness score for all intermediate gas, we combine them together considering a growing weight for modeling our concerned increasingly consistent property. Such obtained final score is normalized between 0 and 1. The closer to 1, the more increasingly consistent the profile is, and the more likely the input be within. Otherwise, it is a beyond 1. Until now, our approach is able to measure the gas profile of any input sample at runtime and gives its score. We experimentally evaluate our approach on several widely used subjects and compare it with two existing techniques. We evaluate on both effectiveness and efficiency. The results show that upon our AUC measurement for effectiveness, Dissection can be quite effective with a nice AUC scores. Also, it shows its superiority ranges and a landslide victory over existing approaches. Concerning the efficiency, Dissector's key input validation part takes only 3 to 4 milliseconds per sample. That is extremely efficient, while the existing approaches take several 10 or hundreds times of large overhead. Even for complex subjects ImageNet and ResNet 101, Dissector still only takes 5.8 milliseconds for validation, while both existing approaches fail to apply. Despite its effectiveness and efficiency, Dissector can also be used in many other areas. In our study, such input distinguishment can also apply to famous adversarial input identification with extremely nice AUC scores. Besides, Dissector can also be used to help isolate the beyond inputs and improve the actual accuracy in use. Moreover, Dissector can also be used as a wrapper to help tolerate imperfect deep learning models. Dissector's usages also gives us an opportunity to seek for a new metric to fairly compare different deep learning models and deep learning scenarios for one model in a quantitative way. Here, we conclude our presentation today. First, we talk about the reliability issues that deep learning applications have and present an input validation way to address this problem. We give our capability scope hypothesis and based on it, introduce how we inspect the gas profile and measuring the input gas consistency. Then, we introduce Dissector's two key tasks and then evaluate its performance. Finally, we talked about the Dissector's potential usage here. Thank you all. That's all for my presentation today.